the expression of the sound wave V equal to square root of B over rho is interesting. We can see that B, which is the bulk modulus of the medium, is an elastic property of the medium, while rho, which is the mass density of the medium, is the inertia property of the medium. So we may write the velocity of the sound wave as a square root of the elastic property over the inertia property. Okay. If we compare this expression with the velocity of wave on a string, okay, if we compare this with the wave on a string, we have that V is equal to the tension over mu. Okay, V is the square root of the tension over mu. And when we compare these two equations, we can see that the tension represents the elastic property of the medium, right? While the mu is a linear density, which represents the inertia property of the medium. So we again have that the velocity of the wave on the string is the square root of the elastic property over the inertia property of the system. And this is the general character of the mechanical wave. That is, the velocity is proportional to the square root of the elastic property over the inertia property of the system. Now, back again to the sound wave. We also have the relation between the velocity of the sound wave and the temperature of the medium. Okay. The speed of sound wave. We can also write it as a V is equal to 311 times the square root of 1 plus T in degree Celsius over 273. This is in meter per second. Okay. We can see that the number 331 here is the velocity of the sound at the temperature in Celsius equal to 0. So the velocity of the sound at the 0 degree Celsius is 331 meter per second. Okay, so from this expression we can calculate the velocity of the sound wave at any temperature. Okay. Also from this relation, we can write down the maximum change of the local pressure of the sound wave delta P max, which is equal to the bulk modulus times the maximum displacement S max times the wave number of the sound wave. But from this relation, from this expression, V equal to the square root of B over mu, we can express B, the bulk modulus, we can express B, the bulk modulus of the medium, as the rho times V square, where V is the speed of the sound wave. So the maximum change of the local pressure is equal to the rho V square times S max. And also we can express the wave number, the angular wave number, as omega over V. Okay, so at the end we will have the maximum change of the local pressure is equal to the rho V omega and S max. Okay, so this equation gives us the maximum or the amplitude of the pressure wave in terms of the density, the velocity of the wave, the frequency, the angular frequency, which closely relate to the frequency of the wave, and the maximum displacement of the medium, which may be more useful than when we calculate it directly from the bulk modulus and or from the bulk modulus of the wave of the medium, because the density of the medium is easier to determine than the bulk modulus. This table gives us some numerical value of the sound wave in various medium. So it is in the gas. We have in the hydrogen, helium. This is in the air in 20 degrees Celsius, and this is in the air in the 0 degrees Celsius, and this is in oxygen. So you can see that the sound wave in the oxygen and in the hydrogen is different from the air, because the velocity of the sound wave in the air is like an average of the sound wave, because in the air is a mixture of many kind of gases. But you can see that this is quite close to the velocity of the sound wave in the oxygen, because there is a lot of oxygen in our air, in the Earth atmosphere. That is necessary for the light form. And also this express the velocity of the sound wave in liquid and also in the solid. The sound move quite faster in the solid than in the air. Okay.